Welcome once again. And we are going to start the second lecture now, which is Beyond Hopfield. And as you can see that this relates more to Professor Vipin Srivastava's own work and hence promises to be even more exciting. So over to Professor Srivastava.
Thank you very much. So to start with, let me express my gratitude to people who have worked with me in this subject. So Sam Edwards, whose name appeared in the previous lecture in connection with the spin glass theory. So Sam Edwards and Phil Anderson were the originators of spin glass theory. David Parker is a neuroscientist at Cambridge. Enzo Granato, together with Enzo Granato, we first started working in this area in Brazil way back in '93. And these are my students, that's my wife. In fact, she initiated me into this subject in Brazil, when we were in Brazil. So as I said in the end of the last talk, that the memory catastrophe spoils the party in the Hopfield network, in that if it puts a serious restriction on the memory capacity, that if the number of patterns exceed 14% of the number of neurons, then the system collapses, the network collapses, and there is no associative memory, right? No matter how, any pattern that you have fed in, none of them can be retrieved. So as I said, 14% of 10 to the 11 is a large number, but what is not acceptable here is that this model brain should break down if it is overloaded. That is the problem here, okay? Now, in the early 90s, a lot of work in the physics domain was done on this particular problem. And so attempt was to see why this happens and how we can overcome this restriction or this problem of memory blackout. So it turns out that the culprit is the fact that the vectors which are being memorized, the patterns or the vectors, have correlations amongst them. And that gives rise to noise. That is, if the vectors dot product is non-zero, then the noise happens, and as more and more patterns are fed, the noise builds up. And at one point, at this critical point, the noise takes over the signal. And so none of the signals can be retrieved. Okay? So so the idea was to, it was quite embarrassing for an otherwise successful, almost the first successful model for cognitive memory by Hopfield. So given that, as I said, a lot of effort was done in the 90s. I have not listed all of those, but this is one of the prominent papers that actually analytically showed the limit of 0.114%. Okay? And together with Enzo Granato and my wife and so on, we tried to give a model which was like a palimpsest, that as new memories come in, the old ones are erased, making room for the new memories. Okay, which is okay to some extent. And in that connection, we also talked about short and long-term memories. Okay, but that we didn't pursue this line much. But at this point, I had a discussion. I was in Cambridge, and Sam Edwards asked me that what is it that people are doing with spin glass ideas world over, and can you explain to me? So I was explaining to him what I explained in the last slide, the last lecture, and then he said that even though the noise, which is because of the similarities between the objects, is spoiling the scenario, but that is necessary. We learn about this chair and we learn about any number of chairs of this, and we immediately recognize that that's a chair, which means that their vectors are overlapping. So overlap is part of the game, or even though it is spoiling the party. So can we have the cake and eat it too? Can we deal with this non-zero vector product and yet have overcome the problem of catastrophe? So it just occurred to us that it could be possible if the patterns as they are coming to be recorded are orthogonalized with respect to each other. Gram-Schmidt orthogonalization, which the physics community knows about. Okay, so that simple idea kind of clicked. So what we suggested was that as the vectors are coming to be recorded in the brain, in the synaptic connections, they are orthogonalized sequentially as in the Gram-Schmidt orthogonalization. Okay, so this was the first time that we gave this idea in 2000. And for those who may not be from physics, orthogonalization means that if you have xi1, these vectors, which are similar in that their dot products are non-zero. Of course, there are other conditions under which they can be orthogonalized. So when they are orthogonalized, they are mutually perpendicular to each other, no overlap, and therefore the noise will disappear. Right? Now it seemed to be too simple an idea. So we tried to go into the depth. So here is the Gram-Schmidt orthogonalization scheme. The first pattern comes and is recorded as it is. The second pattern is orthogonalized with respect to the first one. The third one is orthogonalized with respect to the first three, and so on. So these are the raw vectors, and these are their orthogonalized versions. And we propose that if these orthogonalized vectors are stored according to the Hebb's hypothesis, the interaction Jij as we defined earlier, then the job should be done. So, and that actually worked. So it does. So what it means is essentially that when a new pattern is coming and is being orthogonalized with the previous ones, then what we are doing is we are separating the similarities and differences between them. And what is more, we suggest that orthogonalization means that we are storing these similarities and differences, not the raw vectors or the orthogonalized vectors. I mean, we are storing the orthogonalization vectors, but that amounts to storing similarities and differences. And that too in an economical fashion. I'll come to this very soon. So this is a drastically new thing. And so when we did the competition, it is quite trivial that if we have n neurons, then we can store n patterns. So the memory capacity is 100%. Everything that is being learned, as long as it doesn't exceed the number of neurons, everything will be remembered and retrieved very effectively, very efficiently. Retrieval is very fast. Okay. So insofar as computation is concerned, this was fine. Then as we did the simulations, we realized that what we are storing are these numbers and not plus minus ones. These set of numbers and these set of numbers. That is this vector and this vector in the Hebbian manner. And in this, if you notice that when we orthogonalize these two, these are two very similar patterns, and the amplitudes on the differences is higher. That means if two objects are very similar, then the differences are stored with greater emphasis. Okay? And if the two objects are very different, then the similarities are stored with greater emphasis, which is intuitively quite good. In that, suppose we know about we are familiar with a particular model of a car, and if we see another car of the same model, we don't pay attention to the details, we pay attention to the differences because they are very similar. But we are familiar with cars, and if we come across a very weird looking car, a very weird looking vehicle, and we say that yes, it is an automobile, but it's very different. So there we look at the similarities, that we categorize it as a vehicle because it has four wheels and some such things, and pay more attention to the differences. So this was quite appealing intuitively, right? So orthogonalization seems to, if orthogonalization is a physiological process, if the brain actually uses orthogonalization to store the information, then it is doing it in a very interesting way, in that, I mean, when we say orthogonalization, in simple terms, what we are saying is that the brain is storing similarities and differences in an economical fashion, like this. Okay. So this was a simple idea, and it has a few other cognitively appealing. So now the question is that it is easy for a theoretical physicist to say that brain does orthogonalization. Okay, and that orthogonalization could be a physiological process, but it won't be accepted in the scientific community unless there is experimental evidence to it. There's a neuroscience. If there is a neuroscience, if neuroscience experiments show that this is the case, then only it will be accepted as a physiological process. Okay, not just as an idea in physics. So this was a big challenge, and there's a long story behind it, which I will not tell to save time. But to enter into the domain of neuroscience, first, we had to understand the neuroscience, and that's where David Parker's association with us helped. And I sat down laboriously. I was told that David Marr, a neuroscientist, a formal neuroscientist, had written 3 seminal papers And unfortunately, he died very young, at the age of 35 or so. But those three seminal papers were, were considered very important, but they were very difficult for the neuroscientists because they were formal. So I spent a lot of time deciphering, understanding that one of the three papers, which was on cerebellum. Cerebellum is the part of the brain here at the which is involved in balancing act and so many other cognitive functions. Okay, and in the evolution, this came in the beginning of the evolution of the brain. Okay, so it has so many different types of neurons and the synapses with different properties and so on, which were explained by David Marr and so on. So I tried to cook up a model if for cerebellum to do orthogonalization. If cerebellum were to do orthogonalization, that is, an information comes and another information is to be, the next information is to be orthogonalized, then this is what it would do in different parts, and and these were the proposals made for the biologists, for the neuroscientists. Now, temperamentally, they are all very skeptical people. They wouldn't do experiment just because you say that, test if the Golgi cell multiplies and not adds. There are cells, now it is well understood that there are cells which multiply. Most of all the cells add, but some of the cells add in their language supralinearly, which is like multiplication. Okay, so 2 plus 2 doesn't add to 4, but 2 plus 2 adds to 7. So something like that. So right. So like that we suggested, but then David Parker, who works on a particular, his animal model is lamprey fish. Okay, and he works on the spinal cord of lamprey and so on. So he said that I can do some experiments on lamprey, and which he is doing, and we have published some more things. But what he pointed out was, after looking at this proposal, he said that in a very gross term, this circuitry which you are defining does feed-forward excitation and feedback inhibition. In a very coarse-grained sense, that is what it is doing. And he pointed out that that kind of circuitry, exactly that kind of circuitry, exists in these parts of the brain. I mean, these are hippocampus, I know a little bit, but these are parts of the nervous system which have that kind of circuitry in lower vertebrates and also invertebrates. This is what he said, and there are references to it. So this is what we published in this paper, Journal of Theoretical Biology. So we feel that there is some experimental evidence to show that orthogonalization could be a physiological process. Okay, and that physiological process involves saving of similarities and differences in the synapses, rather instead of the raw complete information about the raw vectors, or even the of the raw vectors. Yeah. Okay. So this gave us some satisfaction that there is some experimental evidence to support that the nervous system, the brain, could be doing orthogonalization, Gram-Schmidt orthogonalization. Okay, so this was fascinating because when Gram and Schmidt developed this orthogonalization, which was more than 150 years ago, they hardly would have realized that the brain perhaps already does orthogonalization. Okay, so this was something which gave us, made us a little more happy. Now, Gram-Schmidt orthogonalization is sequential, right? One vector comes, the second vector is orthogonalized, third vector, and so on. But so that can be good enough for the cognitive processes which are sequential, like language learning and any sequential learning. Okay, but then there are so many non-sequential phenomena in different other types of memories, like episodic memory, in which I remember this whole setting, and any change happens here, I correlate with all the other parameters here. Okay, so those kind of orthogonalizations where they are very familiar to theoretical chemists, but in physics also some work has been done on Lovedean orthogonalization. Parallel Lovedean in Sweden developed two orthogonalizations which are called democratic, in that they take all vectors at the same time and an orthonormal basis is created. Okay. So I discovered some very curious geometrical properties hidden in the canonical and symmetric orthogonalization produced by Lovedean. So this is one area in which a lot of work needs to be done, employing Lovedean orthogonalization to understand certain cognitive phenomena like episodic memory and so many other things. I mean, another thing is like Alan Turing was what do you call, the people who have learning disorder, but there is a name for it. My own memory is deceiving me. Alan Turing had disorder, that disorder. There was this movie made by Amir Khan. नहीं गजनी नहीं, बाद में बच्चे के ऊपर है, सारे जमीन पे, उसमें जो मेंटल जो लर्निंग डिसऑर्डर दिखाया है, dyslexia. So I have a hunch that dyslexia, see the dyslexics are they have learning disorder, but they are outstanding in recognizing patterns. Like Alan Turing himself was dyslexic, and during the Second World War, they were all engaged by army, British Army, to decipher the secret signals. They all have patterns which were deciphered by dyslexics. So I have an intuitive feeling that Lovedean's orthogonalization can help us in understanding. So I am hoping that somebody will get this idea and do some work. Then there are other questions about stability and in the associative recall, etc. These things. Now, the questions are, could orthogonalization be an innate property of the brain? Well, here, the link, this is something which is well known to Chomsky, that what Chomsky found out was, or proposed, was that we are born with competence to learn languages, right? See, the grammar, there is a core grammar which is hardwired in the brain, okay? And depending on the language spoken around a child, so between the age of 12 to 18, the child picks up the grammar of that particular language. So what the linguists tell me is that corresponding to that particular language, which is being spoken around the child, certain switches are turned on in that that particular hardware in the brain. Okay, and the child learns that language. Okay, but there is a core grammar which is common to every language on earth, including the man-made languages like the computer languages that we learn. There is a core grammar which Chomsky says is all pervading. And so in the case of humans, it needs an apparatus that can connect the acquired language with the innate grammar and select and do it economically. So we would like to believe that orthogonalization, which perhaps is also an innate property, could be the tool that the Chomsky mechanism requires. Right. So much for orthogonalization. Now, the question that you raised in the first talk about long-term memory. So all of us have felt it's a common knowledge that we tend to forget, what we had for the breakfast, but we don't forget things that happened in our childhood, right? So obviously, the mechanism for short-term memory and the long-term memory are different. Okay, so now even if there is a trauma, there's an accident, or there's a psychological trauma or something that can destroy some neurons and synapses, but still and that can affect the short-term memory, but long-term memory is not really affected by that to a large extent. So what could be the mechanism involved in the long-term memory storage so that that it is not affected by, that it is robust against trauma? What we have tentatively proposed, not tentatively, we have published it, the theoretical idea, but a lot of work needs to be done to polish it. In broad terms, we are suggesting that the long-term memory has a holographic character. In that, when the information, when the memories, see, all the sense organs take the information to the part of the brain called hippocampus. And that's where the memories are formed. Right? So short-term memory resides in the hippocampus, but then they are transferred to other parts of the brain, particularly the cortex, the surface of the brain, for long-term storage. So long-term storage, the long-term memories reside in the cortex, the surface of the brain. So our proposal is that when the memories go selectively from short-term memory areas to the long-term memory areas, they are Fourier transform. They are Fourier transform. Okay? So that would mean that each neuron has, so to say, information of all the entire memory, the entire information that is being transferred is possessed by each and every neuron. So even if some neurons and synapses are destroyed, the surviving neurons and synapses can still put together the memories, and we have the long-term memory. We don't, right? So this is exactly how the holograms are formed, right? So this is an idea which we have, we started working, we have initially published this, but there's a lot of work to be done. And in order to connect it with neuroscience, which has to be done, otherwise it will remain just an idea. Somebody will have to again do the kind of work that I did with cerebellum, make a model that allows you to do, that allows the neurons and synapses to do Fourier transformation. So that is very tentative. I mean, we just try to do something, but so anyway, so that's where I would like to end this lecture also. Thanks so much.
This optimization, does it have any connection with the Shannon data compression theorem and things like that?
It should be. It should have, yeah. But that's why I said that. You see, there are two sides to Hopfield network. The people who do the computer science kind of applications, they should know about these things as well, in order to see how. See, our mind doesn't work in that way. That how it will find an application. But
I wanted to say was that there is also memory is not just in the brain, there is also called muscle memory. So to make it even more robust, you remember certain things by touching certain parts of signals from the rest of the neural system.
Yeah, so that's why I was saying nervous system, not just the brain. Sorry?
My gut.
Yeah. Yeah.
When child is born, let us say I'm taking the case of an autistic child.
Yeah.
Autism. Up to 3 years, his development is normal.
After?
Up to 3 years, 2 to 3 years to 4 years, the child is normal.
Uh-huh.
As far as his neural development is concerned.
Okay.
Then each of the genes get switched off in some parts of the brain. As a result, he goes down from the optimum period memory to zero memory. This is another case study. Zero memory. But all personality area of real memory about this child. Remember that when they will be here, Professor Srivastava lecture on this case. If I bring him to that this way, and take him like this out of space. These sorts of persons that form an other sample study for story of the case. And I couldn't make out so far as Golgi cells dividing, Golgi cells.
Yeah. I see. Well, that's a neuroscience question. I see. All cells have Golgi. So Golgi is a characteristic or a property. Yeah, but from what I read, when these are the Golgi cell, Purkinje cell, and so many other, yeah.
So it picks up only 1% of the neurons when you stay in the Golgi.
But dividing
see.
one into two.
You say a million of the cells, one
What did I say? Yeah. I didn't get it. Yeah. Yeah. No, I mean, what this requires is that the Golgi cells should be, all the cells receive the information and they add. But this mechanism, if it were to do this part of the calculation, then it should be multiplying the information. Huh.
You think absolutely wrong. A kind of neuron that is next. So that's what. So Golgi in other context is a fetus, but in this context they are saying for an entry neuron.
Super division, one to two.
Division I was
No, not division. I mean, here it is said that it is adding supralinearly. That is 1 plus 1 is 2, you know. But here, when two signals come, the output is more than the sum. So which they take it as multiplication. Yeah. So that's supralinear. Yeah. Yeah.
Biological factor is not memory defect. Some people have better memory, do not have good memory. So what is that makes good memory?
I don't know. See, as I said, these are all very crude toy models. Yeah, okay.
but mathematical faculty, I might have better spatial memory. So everybody's brain is a bit different in terms of my interest and how it develops. And those areas become stronger. And you can say, I cannot say memory could be good in one aspect.
Yeah, no, but he's asking what could be the physiological basis.
Hormones, that area are more active.
Chemical blast, chemical is revised time in the brain. That memory becomes more easily replaceable, and it depends upon the function of one enzyme which we call it.
But दूसरी कहा जाता है जेनेटिक है एक आदमी है उसको मैथमेटिक्स में मेमोरी काम करती है लिटरेचर में नहीं काम करती है तो क्या चीज
language is something which is taught to a child from birth. And children who speak very well are sometimes finding it very difficult to become numerical skills.
Is it right? No, I haven't noticed that. Yeah. Yeah. So you're saying that those who are very articulate, I see. I see.
That's what I'm trying to say.
Numbers right from the plan.
I have no clue. I have no clue.
क्या ब्रेन की फंक्शनिंग को क्या have the scientists been able to decipher the full genetic or biological aspects of brain? Of brain. Why is it that I have better memory than somebody else?
Yeah.
Memory in terms of context. And maybe we cannot say overall.
Then let us say, in the whatever context, let us say, you can appreciate the picture and you still remember. After you get 6 hours to be memory when you are dying, you still have some recollection. So child is selective है, अगर selective है तो क्या ये physiological है या psychological?
These are all very.
Can you think you remember it?
So what is that? What makes the memory?
Right. No, that's what he's asking. What is the physiological basis to it?
Once you know the value of 500 rupee bill, you don't have to be reminded. You will see it from distance. As he said, from the bottle. How the bottle.
Let us say, आपको फिजिक्स अच्छी लगने लगी या लिटरेचर अच्छा लगने लगा, आप अगर दूसरे अगर हिस्ट्री भी पढ़ते हैं तो याद नहीं आता, क्योंकि आप अंग्रेजी पढ़ रहे हैं, तो क्या लगता है?
How repeatedly the concept has been clear and how repeatedly the synapses has been fired, that thing is remembered in life. Yeah,
I want to ask you some different questions.
He remembers first thing, so I remember first thing. I remember the application with the due respect, I bet you state that I'm suffering from fever. Kindly grant me.
That is one time. I won't touch on something different also. So once, like there are tests, if I'm shown a visual with the text, pictures of food items that are sweet, and there's no word sweet when I'm tested, so I'll still pick because all the things that I saw were sweet. They say memory fails at times.
Yeah.
Because you're given a choice of food items that were sweet in taste, you say yes. In the list, there were things like it's called solubility of memory. Memory fails at times.
Okay,
So,
okay.
put in the shots, some experiment. So that's also something very, very interesting. Second
Yeah.
is,
Nice.
इसके इवेंट को हम ज्यादा याद रखते हैं और कुछ इवेंट में याद नहीं.
That's why I said from short-term memory areas, when it goes to long-term memory areas, selectively, one doesn't know how that selection happens. Yeah. I don't know.
So,
I mean, everything is unexplored. We are just scratching the surface, you see. Yeah. So,
Whatever this learning is done, that pattern will be, but whatever we learn, the way we see as to learn, that will be, so like, as you told me, if from beginning child is given numbers, his brain organizes in certain way. But if it is taught language, maybe in another way, and then it tries, then the one with numbers is given language, the model is already created over. So is it possible that they will go along?
oh my God, these are all very subtle questions, and yeah.
As a role to play in training also, where you are able to see that it is really training our mind and helping us to recognize those things which are similar and which are different. Training has something to do with that. For example, if you look at chess players, you will find that they're very clever in seeing the pattern, seeing the differences. So how far this training has something to do with the physiological processes which happen via these neurons, whenever we are talking about machine learning, we are always talking, there is a training set, and then we are going towards
so all this learning means training. Yeah.
So this training, at least you training. When we were talking about those muscle memories, short training, artists say draw daily, and you will find that your hand will work very nicely.
Yeah.
You don't think that it is coming somewhere from my hand.
So in that case, the training is very simple. It's reinforcement.
It is at the heart of that.
I would like to believe that. Yeah. Because when you are training, you are sharpening the similarities and differences. Yeah.
The orthogonal basis you are mentioning.
In connection with brain. In physics. Oh yeah. Whenever you have to create an orthonormal basis.
With a set, you can always do a graphical talk.
Yeah, linearly independent set. Yeah. Loud in one. Yeah. It's of the same kind. Yeah. Yeah, it has a lot of applications. And if you talk to theoretical chemists, they will tell you. But the interesting thing here is that it takes all the vectors at the same time. And if they are linearly independent, then it will give the orthonormal basis in one shot. Whereas Gram-Schmidt is sequential. Yeah.
Can actually also go towards the classification of the organization processes into some kind of that, okay, these processes will help me short term and
I would like to understand that. Yes. I would like to. Yeah.
very interesting
Yeah.
idea of organization
Yeah.
which we
But-
have put forward.
Hmm.
Lot of sense in identifying it.
Yeah, I think so. Yeah. Yeah.
Please take up the hard work time. It is possible to plant it in the way.
Well, Elon Musk is doing it, right? I don't know. You have to talk to neuroscientists. Yeah. They're doing it for, like stroke patients. They replace certain part of the brain with a chip, and that particular function is restored. Yeah. Yeah.
Try to model them using computation. So is there two degrees of freedom that the positions of neurons can change and the length of synapses can change?
Yeah. So, see, that's where the analogy with spin glass work, because there the spins are of various separations. And there it showed that if the separation is very large, then it can be again ferromagnetic or antiferromagnetic. Even if the separation is small, it can be according to that, sinusoidal or decaying sinusoidal thing. So because of that, that accommodates the fact that the synaptic connection can be excitatory or inhibitory. Okay. So the neurons are not moving. They're all fixed in their positions and they form a network. Okay. But in biology, the fact is that a particular synapse is known to be excitatory or inhibitory. Its nature does not change. Its magnitude may change. But in this model, it allows a synapse to be now excitatory and the next moment it becomes inhibitory, which is biologically not feasible. But so, I mean, I don't know whether I answered your question.
Never see neural networks, they are always like connected by straight lines.
Yes.
Can we model them in a way because we can include repeating any curve and then more patterns can be improved like that? The straight lines connecting the neuron.
Actually, straight line is not, it is shown only because of the convenience. But the axon actually can take various shapes. So it is the separation between them insofar as physics is concerned. But in biology, the shape or how much curvature, whether the axon is like this or like that or like that, is not important, I guess. It is the neurotransmitter, the nature of the neurotransmitter, that is important. So in modeling, also it is not really important, the shape of the synapse.
cerebellum tests orthogonalization, physiological.
I did not prove. We tried to model if cerebellum were to do orthogonalization, then its cells and synapses would function like this. That is for the neuroscientists to test whether these cells and these synapses actually work in those fashions. That has, but at that level, it has not been tested yet. In a coarse-grained manner, we see in this that there is a feed-forward excitation and feedback inhibition, okay, in a coarse-grained sense. And that kind of circuit, this circuit, in a coarse-grained manner, boils down to this, that it is feed-forward excitation, feedback inhibition, okay? And that kind of circuit exists in several parts of the nervous system, including spinal cord and yeah.
Same set of information we are presenting in front of two students. One has like sharp memory and another has weak memory. Just this sharp memory or weak memory, somehow there is some correlation with the
I don't know. These are all like, he was asking, what is the physiological basis of sharp memory and weak memory? But I'm sure neuroscientists can give shed some light. Yeah.
Context.
Yeah. Yeah, contextual.
लोगों को जानता हूँ
हाँ
वो दूसरे आदमी को देखता है उससे पूरी पढ़ लेता है और उसका कैरेक्टर बता देता है जैसे कि मैं हिंदी पढ़ रहा हूँ या हिंदी पढ़ रहा हूँ तो याद नहीं रहता अगर मैथमेटिक्स पढ़ता हूँ तो याद रहता है तो कोई तो वजह होगी कोई ना साइंटिफिक एक्सप्लेनेशन होगा इसके
brain is
मैं आपसे क्या इस चीजों का भी रिसर्च करें ये क्या ब्रेन का
I don't know. मेरा ज्ञान तो बहुत ही लिमिटेड है. But cognitive scientists might be, so there are cognitive scientists which are typically psychologists and neuroscientists. So if they work together, then they can address many such questions. Yeah.
Forward and back propagation, which
Huh.
is artificial. Very heavy.
Feed forward excitation, feedback inhibition. Huh. 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 No, that is a different ball game altogether. That is Hinton. They modified the whole architecture of the network. In Hopfield network, the neurons are spread in no particular geometrical manner. They are just spread randomly.
Cognition of promotion lies there. Is that
I don't know. Much simpler than that. Yeah. That's right. Yeah.
Well, this was one of the best lectures that we had.
Really?
I think I'm audible. Yeah. वो भी contextual memory में. They know what to do. ये सुनी सुनाई बातें हैं, हर एक स्पीकर को आप अप्रिशिएट करते हैं।
Friends, you would have everybody has said this is one of the best things. And it has allowed all kind of concern, create about them. जैसे कि memory short हो गई है, ऊपर के साथ काम हो गई है, याद नहीं रहता, तो we all have this kind of patience, not the patience. So this thing, this subject part of the passion of the law. उससे हम आगे को और अच्छा है। So I must have a gentleman on this. And I will remember needed more. That is the book that is and continue to write and get that will defeat. Hopefully we will have it more than two. But our technology allows that you can have your life. But continue to think about this. Because there are three areas we want to and we need to become one great. We want to one is really all of it. Yeah, which is something that we love. In fact, the couple. What is beyond what we did? We the reverse, yeah. In fact, come back. When it comes out, coming to the dialogue, so then it becomes what is one? What and should be the state of and for the something that is started from that. What is the life of
Mike don't know again.
whether the life of the or does it happen? Will it continue to you self-reflect with the limited now, fundamental knowledge, or we are not
उन्हीं का होगा और डेफिनेटली
Thank you. We have completed. You both have to take it. Thank you. And